A pulse jet engine is a type of jet engine in which combustion occurs in pulses. A pulse jet engine can be made with few or no moving parts, and is capable of running statically. Pulse jet engines are a lightweight form of jet propulsion, but usually have a poor compression ratio, and hence give a low specific impulse. One notable line of research of pulse jet engines includes the pulse detonation engine, which involves repeated detonations in the engine, and which can potentially give high compression and good efficiency. Types: there are two main types of pulse jet engines, both of which use resonant combustion and harness the expanding combustion products to form a pulsating exhaust jet which produces thrust intermittently. Valved pulse jets. Valved pulse jet engines use a mechanical valve to control the flow of expanding exhaust, forcing the hot gas to go out of the back of the engine through the tailpipe only, and allow fresh air and more fuel to enter through the intake. The valved pulse jet comprises an intake with a one-way valve arrangement. The valves prevent the explosive gas of the ignited fuel mixture in the combustion chamber from exiting and disrupting the intake airflow, although with all practical valved pulse jets there is some blowback while running statically and at low speed, as the valves cannot close fast enough to stop all the gas from exiting the intake. The superheated exhaust gases exit through an acoustically resonant exhaust pipe. The intake valve is typically a reed valve. The two most common configurations are the daisy valve, and the rectangular valve grid. A daisy valve consists of a thin sheet of material to act as the reed, cut into the shape of a stylized daisy with petals that widen towards their ends. Each petal covers a circular intake hole at its tip. The daisy valve is bolted to the manifold through its center. Although easier to construct on a small scale, it is less effective than a valve grid. Valveless pulse jets. Valveless pulse jet engines have no moving parts and use only their geometry to control the flow of exhaust out of the engine. Valveless pulse jets expel exhaust out of both the intakes and the exhaust, though most try to have the majority of exhaust go out of the longer tailpipe for more efficient propulsion. The valveless pulse jet operates on the same principle as the valved pulse jet, but the valve is the engine's geometry. Fuel, as a gas or atomized liquid spray, is either mixed with the air in the intake or directly injected into the combustion chamber. Starting the engine usually requires forced air and an ignition source, such as a spark plug, for the fuel-air mix. With modern manufactured engine designs, almost any design can be made to be self-starting by providing the engine with fuel and an ignition spark, starting the engine with no compressed air. Once running, the engine only requires input of fuel to maintain a self-sustaining combustion cycle. History: Russian inventor and artillery officer Enter Lesov patented a pulse jet engine in 1864, while Swedish inventor Martin Wiberg also has a claim to having invented the first pulse jet, in Sweden, but details are unclear. The first working pulse jet was patented in 1906 by Russian engineer V.V. Karavodin, who completed a working model in 1907. The French inventor Georges Marconet patented his valveless pulse jet engine in 1908, and Ramon Casanova, in Ripoll, Spain patented a pulse jet in Barcelona in 1917, having constructed one beginning in 1913. Engineer Paul Schmidt pioneered a more efficient design based on modification of the intake valves, earning him government support from the German Air Ministry in 1933. Argus as 109-014 In 1934, Georg Madelung and Munich-based Paul Schmidt proposed to the German Air Ministry a flying bomb powered by Schmidt's pulse jet. Madelung co-invented the ribbon parachute, a device used to stabilize the V-1 in its terminal dive. Schmidt's prototype bomb failed to meet German Air Ministry specifications, especially owing to poor accuracy, range and high cost. The original Schmidt design had the pulse jet placed in a fuselage like a modern jet fighter, unlike the eventual V-1 which had the engine placed above the warhead and fuselage. The Argus company began work based on Schmidt's work. Other German manufacturers working on similar pulse jets and flying bombs were the Asconia Company, Robert Lusser of Fissler, Dr. Fritz Goslar of Argus and the Siemens Company, which were all combined to work on the V-1. With Schmidt now working for Argus, The Pulse Jet was perfected and was officially known by its RLM designation as the Argus as 109-014. The first unpowered drop occurred at Pianema 1/4 NDE on October 28, 1942, and the first powered flight on December 10, 1942. The Pulse Jet was evaluated to be an excellent balance of cost and function, a simple design that performed well for minimal cost. It would run on any grade of petroleum, and the ignition shutter system was not intended to last beyond the V-1's normal operational flight life of 1 hour. Although it generated insufficient thrust for takeoff, the V-1's resonant jet could operate while stationary on the launch ramp. The simple resonant design based on the ratio of the diameter to the length of the exhaust pipe functioned to perpetuate the combustion cycle, and attained stable resonance frequency at 43 cycles per second. The engine produced 2,200 N of static thrust and approximately 3,300 N in flight. Ignition in the AS-014 was provided by a single automotive spark plug, mounted approximately 75 cm behind the front-mounted valve array. The spark only operated for the start sequence for the engine. The Argus AS-014, like all pulse jets, did not require ignition coils or magnetos for ignition, the ignition source being the tail of the preceding fireball during the run. Contrary to popular belief, the engine casing did not provide sufficient heat to cause diesel-type ignition of the fuel, as there is insignificant compression within a pulse jet engine. The Argus AS-014 valve array was based on a shutter system that operated at the 43 to 45 cycles per second frequency of the engine. 3 air nozzles in the front of the Argus AS-014 were connected to an external high-pressure source to start the engine. The fuel used for ignition was acetylene, with the technicians having to place a baffle of wood or cardboard in the exhaust pipe to stop the acetylene diffusing before complete ignition. Once the engine ignited and minimum operating temperature was attained, external hoses and connectors were removed. The V-1, being a cruise missile, lacked landing gear. Instead, the Argus AS-014 was launched on an inclined ram powered by a piston-driven steam catapult. Steam power to fire the piston was generated by the violent exothermic chemical reaction created when hydrogen peroxide and potassium permanganate are combined. The principal military use of the pulse jet engine, with the volume production of the Argus AS-014 unit, was for use with the V-1 flying bomb. The engine's characteristic droning noise earned it the nicknames Buzz Bomb, or Doodlebug. The V-1 was a German cruise missile used in World War II, most famously in the bombing of London in 1944. Pulse jet engines, being cheap and easy to construct, were the obvious choice for the V-1's designers, given the Germans' materials shortages and overstretched industry at that stage of the war. Designers of modern cruise missiles do not choose pulse jet engines for propulsion, preferring turbojets or rocket engines. Wright Field Technical Personnel reverse engineered the V-1 from the remains of a V-1 that had failed to detonate in Britain. The result was the creation of the JB-2 Loon, with the airframe built by Republic Aviation, and the Argus AS-014 reproduction pulse jet power plant, known by its PJ-31 American designation, being made by the Ford Motor Company. General Henry Harley Hap Arnold of the United States Army Air Forces was concerned that this weapon could be built of steel and wood, in 2,000 man-hours and approximate cost of $600. Operation. Pulse jet engines are characterized by simplicity, low cost of construction, and high noise levels. While the thrust-to-weight ratio is excellent, thrust-specific fuel consumption is very poor. The pulse jet uses the Lenoir cycle which, lacking an external compressive driver such as the Otto cycle's piston, or the Brayton cycle's compression turbine, drives compression with acoustic resonance in a tube. This limits the maximum pre-combustion pressure ratio, to around 1.2 to 1. The high noise levels usually make them impractical for other than military and other similarly restricted applications. However, pulse jets are used on a large scale as industrial drying systems, and there has been a resurgence in studying these engines for applications such as high-output heating, biomass conversion, and alternative energy systems, as pulse jets can run on almost anything that burns, including particulate fuels such as sawdust or coal powder. Pulse jets have been used to power experimental helicopters, the engines being attached to the ends of the rotor blades. In providing power to helicopter rotors, pulse jets have the advantage over turbine or piston engines of not producing torque upon the fuselage since they don't apply force to the shaft, but push the tips. A helicopter may then be built without a tail rotor and its associated transmission and drive shaft, simplifying the aircraft. This concept was being considered as early as 1947 when the American Helicopter Company started work on its XA-5 Top Sergeant helicopter prototype powered by pulse jet engines at the rotor tips. The XA-5 first flew in January 1949 and was followed by the XA-6 Buck Private with the same pulse jet design. Also in 1949 Hiller Helicopters built and tested the Hiller Powerblade, the world's first hot cycle pressure jet rotor. Hiller switched to tip-mounted ramjets but American Helicopter went on to develop the XA-8 under a U.S. Army contract. It first flew in 1952 and was known as the XH-26 jet jeep. It used XPJ-49 pulse jets mounted at the rotor tips. The XH-26 met all its main design objectives but the Army cancelled the project because of the unacceptable level of noise of the pulse jets and the fact that the drag of the pulse jets at the rotor tips made a rotation landings very problematic. Rotor tip propulsion has been claimed to reduce the cost of production of rotary wingcraft to 1/10 of that for conventional powered rotary wing aircraft. Pulse jets have also been used in both control-align and radio-controlled model aircraft. The speed record for control-align model aircraft is greater than 200 miles per hour. A free-flying radio-controlled pulse jet is limited by the engine's intake design. At around 450 km per hour most valved engines' valve systems stop fully closing owing to ram air pressure, which results in performance loss. Variable intake geometry lets the engine produce full power at most speeds by optimizing for whatever speed the air is entering pulse jet at. Valveless designs are not as negatively affected by ram air pressure as other designs, as they were never intended to stop the flow out of the intake, and can significantly increase in power at speed. Another feature of pulse jet engines is that their thrust can be increased by a specially shaped duct placed behind the engine. The duct acts as an annular wing, which evens out the pulsating thrust, by harnessing aerodynamic forces in the pulse jet exhaust. The duct, typically called an augmenter, can significantly increase the thrust of a pulse jet with no additional fuel consumption. Gains of 100% increases in thrust are possible, resulting in a much higher fuel efficiency. However, the larger the augmenter duct, the more drag it produces, and it is only be effective within specific speed ranges. Function. The combustion cycle comprises 5 or 6 phases depending on the engine: induction, compression, fuel injection, ignition, combustion, and exhaust. Starting with ignition within the combustion chamber, a high pressure is raised by the combustion of the fuel-air mixture. The pressurized gas from combustion cannot exit forward through the one-way intake valve and so exits only to the rear through the exhaust tube. The inertial reaction of this gas flow causes the engine to provide thrust, this force being used to propel an airframe or a rotor blade. The inertia of the traveling exhaust gas causes a low pressure in the combustion chamber. This pressure is less than the inlet pressure, and so the induction phase of the cycle begins. In the simplest of pulse jet engines this intake is through a venturi which causes fuel to be drawn from a fuel supply. In more complex engines the fuel may be injected directly into the combustion chamber. When the induction phase is underway, fuel in atomized form is injected into the combustion chamber to fill the vacuum formed by the departing of the previous fireball. The atomized fuel tries to fill up the entire tube including the tailpipe. This causes atomized fuel at the rear of the combustion chamber to flash as it comes in contact with the hot gases of the preceding column of gas. This resulting flash slams the reed valves shut or in the case of valveless designs, stops the flow of fuel until a vacuum is formed and the cycle repeats. Valve design. There are 2 basic types of pulse jets. The first is known as a valved or traditional pulse jet and it has a set of one-way valves through which the incoming air passes. When the air fuel is ignited, these valves slam shut, which means that the hot gases can only leave through the engine's tailpipe, thus creating forward thrust. The cycle frequency is primarily dependent on the length of the engine. For a small model type engine the frequency may be around 250 pulses per second, whereas for a larger engine such as the one used on the German V-1 flying bomb, the frequency was closer to 45 pulses per second. The low-frequency sound produced resulted in the missiles being nicknamed buzz bombs. Valveless design. The second type of pulse jet is known as the valveless pulse jet. Technically the term for this engine is the acoustic-type pulse jet, or aerodynamically valved pulse jet. Valveless pulse jets come in a number of shapes and sizes, with different designs being suited for different functions. A typical valveless engine will have one or more intake tubes, a combustion chamber section, and one or more exhaust tube sections. The intake tube takes in air and mixes it with fuel to combust, and also controls the expulsion of exhaust gas, like a valve, limiting the flow but not stopping it altogether. While the fuel-air mixture burns, most of the expanding gas is forced out of the exhaust pipe of the engine. Because the intake tube, also expel gas during the exhaust cycle of the engine, most valveless engines have the intakes facing backwards so that the thrust created adds to the overall thrust, rather than reducing it. The combustion creates two pressure wavefronts, one traveling down the longer exhaust tube and one down the short intake tube. By properly tuning the system, a resonating combustion process can be achieved. While some valveless engines are known for being extremely fuel-hungry, other designs use significantly less fuel than a valved pulse jet, and a properly designed system with advanced components and techniques can rival or exceed the fuel efficiency of small turbojet engines. In 1909, Georges Martinet developed the first pulsating combustor without valves. It was the grandfather of all valveless pulse jets. The valveless pulse jet was experimented with by the French propulsion research group SNECMA, in the late 1940s. The valveless pulse jet's first widespread use was the Dutch Droneviolander AT-21. A properly designed valveless engine will excel in flight. As it does not have valves, ram air pressure from traveling at high speed does not cause the engine to stop running like a valved engine. They can achieve higher top speeds, with some advanced designs being capable of operating at Mach 0.7 or possibly higher. The advantage of the acoustic-type pulse jet is simplicity. Since there are no moving parts to wear out, they are easier to maintain and simpler to construct. Future uses. Pulse jets are used today in target drone aircraft, flying control line model aircraft, fog generators, and industrial drying and home heating equipment. Because pulse jets are an efficient and simple way to convert fuel into heat, experimenters are using them for new industrial applications such as biomass fuel conversion, boiler and heater systems, and other applications. Some experimenters continue to work on improved designs. The engines are difficult to integrate into commercial manned aircraft designs because of noise and vibration, though they excel on the smaller-scale unmanned vehicles. The pulse detonation engine marks a new approach towards non-continuous jet engines and promises higher fuel efficiency compared to turbofan jet engines, at least at very high speeds. Pratt & Whitney and General Electric now have active PDE research programs. Most PDE research programs use pulse jet engines for testing ideas early in the design phase. Boeing has a proprietary pulse jet engine technology called Pulsejet thrust augmenter, which proposes to use pulse jet engines for vertical lift in military and commercial VTOL aircraft. See also, Pulse Detonation Engine, Valveless Pulse Jet, List of aircraft engines. Notes. References: Aeronautical Engineering Review, Institute of the Aeronautical Sciences, 1948, Volume 7. George Mindling, Robert Bolton, U.S. Air Force Tactical Missiles, 1949–1969, The Pioneers, Lulu.com, 200, ISBN 0-557-00029-7 pp 6/31. External links: an international site dedicated to pulse jets, including design and experimentation. Includes an extremely active forum composed of knowledgeable enthusiasts, a site for hobby jet propulsion, specifically valved and valveless pulse jet engines. They offer many free Pulsejet plans, and have a lot of useful information. Video of 21st-century built German reproduction Argus as 014 Pulsejet testing, a detailed guide documenting all the steps required to build one's own Pulsejet. The example created on this site is eventually mounted onto a home-built cart and tested. Pulsejets and aeromodels, Popular Rotorcraft Association, Pulsejet Bike, Apocalyptic Robotics Performance Group Survival Research Labs operates a collection of Pulsejet engines and some of their creations, including the Hovercraft, V1, and the Flame Hurricane. PETA article, Ramon Casanova's Pulsejet, American Helicopter XA-5 Flight.